Well, hello, everybody. I hope you can hear me. We are just waiting for a few more people to join, so we will kick off in just a moment. My name is Quentin. My role here is to do the equivalent of announcing where the fire exits are if we were in a real lecture hall. We are recording this. We hope to make it available in a couple of days' time from the page on the lab website. You've probably seen the note. I've done a short URL for that. If you go to tinyurl.com/Wheeler2020, you should be able to find the details of this talk. But you can also find it by going to the departmental website and looking for seminars and looking for the Wheeler series there. We hope to have some questions at the end because there are now, a few hundred of us here. I think the logistics require that we will just do this via the question and answer window, which you should be able to get at from the bottom of your Zoom screen here. And we will be collating questions from there into another document. Apologies if yours doesn't get asked. You may not see any confirmation on your screen that we have read it, but I promise you we have. We will be collating a selection of them into another document ready for the end of the talk. And I think that's quite enough from me. I would like to hand over to Anne Copestake, who is the head of the department, to introduce our speaker for today. Anne, over to you.
Thank you very much, Quentin. So, welcome everyone to the 9th of the annual Wheeler Lectures. This is the first such event to be held entirely online. Since I had to make a visit to the building anyway, I thought I would actually do this intro from Lecture Theatre 1 and give you a live glimpse of it. So, here's where you should be. But actually, the fact that we're forced to do this online has been, in some ways, very helpful because we couldn't possibly have got 500 people in Lecture Theatre 1. And, maybe Lecture Theatre 1 is going to be obsolete technology soon. We don't know. Anyway, we have 500 people signed up for this, and that's great. It's wonderful to see you all, at least in some sense of see you. So, the Wheeler Lecture is the department's most important event. It celebrates the life of David Wheeler and his immense importance, immense achievement as a founder of our field. I'm delighted that Joyce Wheeler can join us today. I don't know whether we can get her on the webcam, but...
Hello, can you hear me?
I can hear you. It's lovely to see you, Joyce. I'm very sorry that we can't actually see you in person and go to dinner.
I should have been. I am there now, I think.
Yeah.
Oh, well, this is very exciting. I'm so pleased to be able to join you all. I think as David was such a pioneer in so many fields, he would be delighted to think that this was the first occasion for his lecture to be given in this manner. Thank you so much.
Thanks very much, Joyce. So even though this is something, a very weird set of circumstances, I think there are some advantages to the fact we're doing this online. Anyway, our speaker today is someone whose influence on computer science and technology is immense, Sophie Wilson. I'm going to keep this short because I think that the best speakers hate long intros because it gives them less time to talk. So I'm going to just take a couple of minutes to highlight some of Sophie's achievements. Sophie was recruited by Hermann Hauser immediately, I think, after graduating from Cambridge and joined the company that very soon became Acorn. I've heard various versions of how Acorn came to get the contract for the BBC Micro. It's a story that's become a bit of a legend, and as I say, different versions are around, but in all versions, Sophie and Steve Furber designed and created a prototype under the most ridiculously intense time pressure. The BBC Micro was how many people in the UK and elsewhere learned about computers in the first place. But Sophie's achievements, that would be enough for most people, but Sophie's achievements went on and on. Sophie and Steve Furber later co-designed the ARM processor. ARM originally stood for Acorn RISC Machine. And that's been the starting point of an extraordinarily successful line of devices. The ARM website says there are 160 billion ARM-powered chips that have been sold. So several of the later ones, not just the first one, several of the later ones were also designed by Sophie. By 1999, Sophie had developed the Firepath processor, and she and 6 others founded Element 14 to exploit this for ADSL. Broadcom then bought Element 14, and Firepath now powers much of the global broadband DSL infrastructure. So an immense set of achievements, and these are recognized. Sophie is a Broadcom Fellow and Distinguished Engineer, a Fellow of the Royal Society, and of the Royal Academy of Engineering, and of the British Computer Society, and of the Women's Engineering Society, and she's also an Honorary Fellow of SELWyn. She has an honorary doctorate from Cambridge and was recently awarded a CBE. So we're immensely happy that she's able to give the Wheeler Lecture this year on the future of microprocessors. And I'll stop and hand over to Sophie.
Right. Under unique circumstances, this is a lecture that has grown with the years. It's never been delivered like this before, so there may be a few halts and pauses when I get things wrong. Okay, the future of microprocessors. So 40 years since it's introduced, the microprocessor has become about 10,000 times faster and billions of times more common, well, hundreds of billions of times more common, just counting the arms. And the world relies on them. We wouldn't be able to do this lecture today if it weren't for microprocessors and signal processors, the DSL link that's carrying my words to you. Everything in our lives is run by microprocessors. So we'll look at how we got here and what the future might look like. And for the mathematically challenged, a little warning, there'll be laws and there'll be one equation in the whole thing, so that's not too bad, and there'll be some graphs and charts. So the first law is really, really obvious, but it's not a law. So Gordon Moore made the empirical observation that while he was working in Intel, if he counted the number of transistors on a manufacturable piece of silicon, then the number doubled about every 2 years. When he first proposed the law, he actually said about every year and revised it several times after that. So about every 2 years was his law. And the chart shows Intel and Motorola processors essentially obeying the law. A long line of devices over 40 years where the number of transistors has gone up over time. Now, not entirely surprising that this law would be obeyed because it was taken as the driving force for the development of silicon manufacturing. So at the time, the International Technology Roadmap for Semiconductors, an organization, had as its mission, make sure that Gordon Moore's law becomes true. And it's now been replaced by another consortium, the International Roadmap for Devices and Systems, IRDS, instead of ITRS, and they still want this law to become true. Obviously, at some point, we'll be down to dimensions where it won't work, but that's cutting to the chase. So the law has a profound impact on all aspects of processors. So as Anne mentioned in the introduction, Steve Furber and myself were responsible for designing the first ARM. It was designed in a 3-micron process. 3 microns nowadays sounds like it's enormous, but 3 microns at the time. And obeying the law, making smaller and smaller transistors, means that we can have smaller and smaller microprocessors of equivalent functionality. So the big plot on the wall is a plot of ARM1 in the 3-micron process, and to the same scale in my hand is a plot of the ARM Cortex M0 Plus, which is the closest modern equivalent to the functionality of ARM1, and it's that small black dot. It's about 70,000 times smaller. So one of the reasons why microprocessors are so common is that they've become so cheap to manufacture. You can have so many of them. So if we look back in time, the first microprocessor that I was involved with in great detail, the 6502, used 4,000 transistors to make it. And on this slide, we have an interesting story to tell. And again, don't worry, there won't be questions about this after the event. So on the left side is a picture of the 6502. When we take pictures of microprocessor die, we like to shine strange lights on it and make different colors. So the yellows, the reds, the greens, the blues are all produced because we shone strong and multi-source white lights onto the original die. So blue is what happened when we shone transmissively through the silicon. Green is what happened when light was diffracted, and I think the red light is also a diffraction, and the yellow is where light got refracted through the silicon, bounced back. So the colours aren't real, they just sort of expose different features. If you looked at it in ordinary light, it would be a very dull, coppery coloured piece of stuff just sitting there, and with the naked eye you'd be able to detect some of the features on this picture. The black things at the edges of the picture are pads where wires are connected to, and the wires are very fine wires. This thing's quite small. Now on the right hand side of the picture is the circuit diagram of the 6502. So everything on that circuit diagram is obviously reflected in the actual layout of the processor. And the circuit diagram has been topologically distorted to make it match the final layout. So you wouldn't necessarily think of the circuit diagram this way normally, but it's interesting to do it like that. So that big green area at the bottom of the picture of the die, that's the 6502's main instruction decoder. That's a PLA, a programmed logic array. And so on the circuit diagram, that's simply a grid of wires with a connection or not a connection to drive the PLA. So you can see the correspondence there, and you can see where there are buses in the circuit diagram. You can sort of see that there are black gaps down the left-hand side to correspond to that big black line, which is an 8-bit bus. And you can make out where there are sort of regular patterns and irregular patterns. Now, obviously, we don't go around designing microprocessors thinking of them as a sea of transistors. Even with 4,000 transistors, it's very unwieldy. Normally, when we design microprocessors, we think of them as arrays of functionality boxes connected by wires. So this is what you normally see for our microprocessor internals. So a 6502, when it was originally released, it ran at 1 megahertz in the Apple II and the Acorn Atom. And when the BBC Microcomputer came out, we got a 2 megahertz one, twice as fast. 4,000 transistors is enough for reasonably sophisticated 8-bit operations, but only 8-bit operations. It would be really quite hard and probably unrewarding to try and design a 32-bit processor with only 4,000 transistors. You'd not have space for anything. When it was designed, it was built in something that was called a 6-micron process and was 21 square millimeters in size. So the block diagram on the right single black lines are just a signal, and thicker, more blocky lines are 8-bit buses. So this is an 8-bit processor. All its internal blocks are connected up by 8-bit buses and controlling signals. So in the middle, there's accumulator A, where a lot of the work of the processor was done. My typical operation on the left, add with carry 9, has to read a value out of the accumulator, add something to it, and write back into it. So the accumulator comes out into the ALU above it, is operated on, and is passed back into the accumulator at the end of the operation. And all instructions are built up like that. The control logic of the processor makes the blocks work together in order to produce the desired architectural answer. So obviously quite successful machines, Apple II and BBC Microcomputer, were built using the 6502. But sort of, what's it like? What did you get out of it? So if we have a typical bit of program, which we'll use for discussing all these microprocessors, we'll just have a bit of C with int A, B, C, add two 32-bit integers A and B together to produce a third 32-bit integer. So that's all we write down, dash it off in C or the programming language of your choice, and then the compiler has to produce the machine instructions that make it work. So 32-bit integer on an 8-bit processor, we're going to have to take it 8 bits at a time. So the 6502, we can load a value directly into the accumulator, and we can also add a value into its accumulator directly. So the address of A, we can load the contents of that, put it into the accumulator, and then we can directly add the contents of the address of B to the accumulator and store the accumulator into C. And then we can repeat that fundamental block for the 4 times that it takes us to do a 32-bit add. So that's quite cumbersome, and it gets even more cumbersome if the compiler didn't know the address that it was using, the things that I've called address A, B, C. If they weren't known at compile time, then the pointer arithmetic in the machine is 8-bit only and gets very difficult. So the best case for the 6502 executing that is 26 cycles. Some of the transistors in the 6502 were spent on achieving that. The 6502 has partially pipelined execution. So while it is completing the operation of the preceding instruction, it's already getting the next instruction into itself, which made it significantly quicker than many of the machines of the same date. But Gordon Moore's going to turn his magic handle. We're going to get given more transistors to play with, build a better micro. So what can you do with more transistors? So this is ARM. On the right is our favoured die shot of ARM1. On the left is Steve Furber's original pencil sketch of where all the blocks that comprise the processor were going to fit and be laid out. And it's immediately obvious that compared with the rather chaotic nature of the 6502, when you look at it from the top, the ARM, it looks like it's designed in a whole different way. Things are very regular and structured, and obviously so. And this is partly because the 6502 was designed by electrical engineers and laid out by hand. They had a big drawing board with a large piece of translucent paper on it, and they stuck rubylith strips on it where they wanted particular metal or polysilicon features for each layer of the processor. And all of that was done by hand for the 6502. ARM was implemented in a structured way on workstations using electronic design software, and it was still laid out by hand, but in a regular way. The other aspect that makes the two processors miles apart is, as signalled in its name, ARM is Acorn RISC machine, where RISC stands for Reduced Instruction Set Complexity Computer, my preferred use of it. The complexity of execution of instructions on the ARM is dramatically reduced compared with that on the 6502. If we look at the internals of the ARM, there isn't actually much to see there. On the right-hand side is the original picture in the data book. It's a set of blocks connected together. The buses are now fatter, they're 32-bit buses, but you know, it's not a million miles away from the picture you just saw of the 6502. To a certain extent, all processor pictures that can be put onto a slide are like this. You never learn anything much nowadays because it's just a sequence of blocks connected together by buses, and you don't get to see more. So we have a smaller process, 3-micron process for the first ARM. That meant the transistors went faster and that we could have more of them. So this processor ran at 8 megahertz when it was first released, and a lot of that is the fact that transistors run faster, but the rest of that is that we could spend more transistors on having a fully pipelined microarchitecture in order to make it run faster. And emblematic of that is that an operation on ARM, typical add operation, add R1 to R2 and put the result in R0, takes just one apparent clock cycle. Obviously, it still takes multiple phases. We have to fetch the instruction, get the values of R1 and R2 out of the register bank, send those values to the 32-bit ALU, in ARM's case, but via the shifter, and then send that value back to the register bank. So we had to take multiple steps at it, but crucially we put enough transistors into the machine that we could start a new one of those every cycles. So that add takes 3 cycles to actually execute, so 3 cycles of latency, but a new one can start every single cycle on the machine. You can literally have back-to-back adds, adding dependent data, and run them continually at 8 megahertz, 1 cycle per instruction. It was a little bit larger than a 6502, 37 square millimeters, but that's not large as far as chips go. Even at the time, it's not large, and nowadays that's considered quite small. When we look at our piece of C, obviously making our processor 32 bits in size means that we only need to do something once to add 2 32-bit integers together to produce a third. But we can no longer operate on data until it is moved into registers in the processor. So in order to get the pipeline in order to get the fast execution of the machine, in order to get the simplification of construction of the microarchitecture, it's a RISC processor with a load store architecture. So that actually increases the number of instructions that we need compared with non-RISC processors, but the instructions are much, much simpler and run much, much faster. So you can just have a pointer sitting in a register, you load from it you load the other data, you add them together and you store them out. Coding very much easier, compiler very much easier, and there isn't this problem that the 6502 had of different styles of how addressing works. There's only one style of addressing, you have to use it. The very first ARM could do this in 9 cycles, so it runs 4 times faster than the 6502, and where the 6502 took 26 cycles, ARM took 9 cycles, so it was 4 times faster on clock rate and 3 times faster on cycles to get the same piece of work done. So 12 times faster, a whole 10x in improvement in performance just for that sort of thing. Now, obviously, this instruction set has managed to survive miraculously to this day. A modern implementation of the instruction set can execute this sequence and complete it in effectively, it's all pipelined and overlapped with other things, in only 2 cycles. So that provides another 4x improvement. So you might say, well, microprocessor architecture, that's so over. You didn't need to spend the last 40 to 50 years of your life doing it. But we get new numbers of transistors every year or two. What's economic to do keeps changing. So what happens when we're given vastly more transistors and we can spend them on architecture? So this is 6 million transistors. So Firepath, as Anne said in the introduction, was the next processor I did. It happens to be the processor that runs most of the world's DSL infrastructure. So not necessarily in your home will you have a Firepath, but at the other end of the line, the green box on the corner of your street or the telephone exchange, it will be packed with Firepath processors running your DSL lines. So 6 million transistors, the clarity of the picture changes. The big orange bars on the right-hand side are Firepath's register file, which is quite a large percentage of the machine. And then you can basically see that there's some structure and a sea of goop. Transistors are too small for optical imaging at this stage, but also we've given over the layout of the transistors that was nice and regular on ARM1. That's now all handled by silicon synthesis, so-called silicon compilers, rather than being touched by hands, and only the sort of macro layout of blocks of the processor has been set in place by a human. Otherwise, the compiler just got to play and put transistors anywhere. And the block diagram of the processor doesn't look staggeringly different. I mean, all the big data buses in this machine are 64 bits in size, and there's a lot of replication of stuff. With lots of transistors, you can afford a lot of replication. We've got faster transistors. This is a 0.13 micron process. So we got faster transistors. We got lots of transistors, so we could afford to burn a lot of transistors in making sure the processor ran really, really quickly. So this thing is 9 stages of in-order issue, out-of-order, complete pipeline running at 330 megahertz. And the surprise is what you can burn transistors on at the instruction set level. So this processor is designed to execute complicated instructions. So the line that says add word R0, R1, which is the destination, R2, R3, R4, R5, colon, LDL2, R6, R7, R8, that's one instruction to the processor. We have to break it down into logical steps for humans, but to the processor, that's one instruction. It does 32 8-bit operations or 4 64-bit operations, or in this case, 8 32-bit operations in a cycle. And it is completely pipelined. Even the loads don't stop this machine. If a load is slow, the machine's in order, issue, out of order, complete aspects take over. And it can maintain that sort of work forever. If it couldn't do that, it wouldn't be able to run the DSL. When we look at your piece of C, then there's some disappointment. We burnt a lot more transistors. We went from the sort of 25,000 transistors on ARM to 6 million transistors on Firepath. And this is just the processor. We're not measuring any transistors in caches or local memories. And if we look at our add two 32-bit integers to produce a third, ARM and Firepath seem to produce much the same program, except I was able to write the two loads to run in explicit parallelism. And of course, invisible is that Firepath is executing things with a 64 bits packed SIMD execution engine, so it does 32-bit, two 32-bit adds in what we wrote. Some of the time that's not useful. So in terms of executing a piece of C, it's not an amazing improvement over an ARM or any other RISC processor for that matter. But in terms of executing signal processing or short vectors, the processor can do an awful lot more work. At the bottom of the slide, we show a typical bit of a signal processing algorithm. So we're doing 4 32-bit loads and multiplying 4 pairs of 32-bit values together, and it can do that and sustain that at the rate of one of those instructions per cycle. So it can get an awful lot of work done inside DSL worlds. So it's kind of obvious, therefore, that if we're given more transistors and can spend them on processor architecture, we can design things that get further and further away from what you normally write in a piece of C. And we can apparently do that without limit. They're actually, you know, if you're designing for special purpose stuff, you can make use of the transistors. If you're designing just to execute pieces of C, it's very difficult to make use of extra transistors beyond a certain point. So the natural reaction to being given more transistors, which obviously as a processor designer, you're given more transistors every time you blink, is to use multiple of them. So this is a DSL central office chip. It's got 2 Firepaths on it. The big slabs of color are the big uniform slabs are memories. The stuff with chaos inside is actual functional logic. And the orange and red areas are where masses of buses run over the tops of memories. So more transistors means not better processors for executing C or even for executing special purpose things. Give us more transistors and you get more microprocessors. The next DSL central office chip along has 4 Firepaths on it instead. Now, that would be good. Smaller transistors means more microprocessors is something that the industry is well behind, and on your typical phone chip, you get now uncountable numbers of processors. Nobody really knows how many are on there. But we come now to our second law. The speed up of multiple processors working on a single problem is limited by the sequential part of the program. And there's an equation. It's the only equation in the entire presentation. So for the math phobic among you, you have nothing more to worry about. But we spell out the consequences in the graph on the right. Let's say we have an absurdly parallelizable problem. Ray tracing, making a Pixar movie, is an absurdly parallelizable problem. So my definition of absurdly parallelizable is that it's 95% parallel and just 5% sequential. And obviously for ray tracing, the actions of tracing each ray over the database is independent, but then you have to collate things back together to make a single frame of your output movie. So that's where the sequential bit gets in. So with a 95% parallelizable problem, what does Amdahl's law say about it? It's the green line. As you increase the number of processors, boy, things go faster nicely. As you keep increasing the number of processors, then the speed up tends to stop. On this graph, the horizontal scale is logarithmic. Every division is a doubling by 2 of the number of processors. And the vertical scale is just ordinary, non-logarithmic. So you can see with a 95% parallel program, we stop at 20x speed up. By the time you've used 1,024 processors, it really isn't mattering how many you have because you just don't go any faster. Now, most people would be really happy to have a 95% parallelizable program to execute. What we see when we look at, say, our mobile phone, you've been sold 4, 6, 8 big apps processors on those things in order to run lots of stuff. In your laptop, there's a continuous war between Intel and AMD about how many processors that you shall be given. You're sort of given at least 4, even if they're virtual processors, at least 4 hardware threads of execution are offered, and we're in the process of seeing that expand to 8, 16, etc. And there's not a lot. I mean, 90% parallel work is very rare. You don't find that level of parallelism in your general loads. 75% parallel work, you might find that in, say, a web browser. It can send off different threads and go and fetch images and think about things separately. But the 75% parallel curve is already really sharply limited to a speed up maximum of 4. If you're writing compilers or sort of general purpose operating system software, you sort of dream of having something that you can make 50% parallel, and there the speed up factor is topping out at a maximum of 2. Amdahl's law is a real law. That's why it's got an equation, and it has very pernicious effects on the design of systems that carry out parallel processing to achieve a single result. Nevertheless, the industry can and will continue to make hardware that has ever increasing amounts of parallel computation ability, both by using multiprocessors and assembly data types and vectors. And of course, traditional scalar computation has not increased very much in the meantime. Indeed, on the desk next to me over there, I have a laptop that I bought in 2006, which runs at 2 gigahertz. And there's no reason to retire it. It's not staggeringly slow compared with modern laptops. Indeed, many of the modern laptops are running with clock speeds that are slower than it. What distinguishes the old laptop from the modern ones is how power efficient they are. So scalar programming languages are a really poor fit to the parallel hardware that the industry is bent on selling you. And we don't have automatic conversion. You can't say, I've got this scalar problem, please take it through your magic tool chain and make it be parallel. That just doesn't work. Human beings need to restructure how they write software, and they aren't doing. We need a big revolution in software to make use of this multiprocessor hardware, multiprocessor parallel hardware. It's just not happening fast enough. So if that was the only problem, I think the future would be depressing in the extreme. Of course, it's not the only problem. This is the severity of the problem is actually getting worse. So if we look back over the chart that I showed you at the beginning, and we annotate it a bit more, we see a period, 1978 to 1986, there was no microarchitecture revolution. Transistors just got faster, but people built things in exactly the same way. So we saw an increase at about 25% a year. So it was worth buying new computers reasonably frequently in those days, but not staggering. Then we went into this period, 1986 to around the 2003 mark, where computers went obsolete really fast. If you waited a year, you could get something that could be up to 2 times more powerful than the one that you had been using. And that was propelled by microarchitecture work, a thing called Dennard scaling, which I won't talk about, but you can go out and look up, and ever more sophisticated internal microarchitecture techniques, such as the in-order issue, out-of-order execute that I talked about very briefly, another thing that you could go and look up. And then we kept throwing transistors at it, and remember that the transistor rate of increase is very fast, really. And we were still making machines that went quicker using out of order and then multi-core machines. And that was becoming a big limit. That 23% a year period from 2003 to 2011, it wasn't that worth buying new computers then. Then Amdahl's law really started to bite. The effect of going from 1 core to 2 core was very noticeable. The effect of going from 2 to 4, less noticeable, and so on. So again, things slowed down an awful lot. And now we're on this plateau, about 3.5% a year, mostly caused by re-engineering transistors a bit to make them a tiny bit faster, getting a little bit more power efficiency and going back and revisiting some of your earlier decisions. We really have hit a state where you could buy something in 2015 and it could still be state of the art today. And that's in spite of consuming vast numbers more transistors, that you just aren't getting the performance gains. So that's painful. And then we have more problems. So we've obviously been using a lot of transistors, and those transistors have been getting smaller, so the resistance and the capacitance figures for each transistor has been dropping, and we've been dropping the voltage for quite a while, but we use so many more of them, and they're in such a small space that things get hot. So this charming graph shows the power density in terms of watts per square centimetre. So against traditional things. So as we went up, Intel 386, Intel 486, Pentium Pro, that was getting quite hot. It's as hot as a hot plate. If you had enough Pentium Pros arrayed together, you could fry an egg. Pentium 2, Pentium 3, and then things went off sideways. Pentium 4 didn't quite get to nuclear reactor levels of heat, and rocket nozzles remain a long way off. Intel, in fact, had to go all the way back to fundamentals. So the Pentium line had built on its own internal architecture, Pentium, Pentium Pro 2, 3, Pentium 4, Pentium 4D. They were a successful microarchitecture until you considered power and power density. Then Intel had to go back and start again and design the thing C2D on the slide, Core 2 Duo, that was a more efficient way of doing things. And that's the ancestor of all the Intel Core I processors today. And even so, they haven't managed to improve the power density that much. They're still running at rather high power density. And the power density is now so high, particularly in mobile devices, but also now in laptops and desktops, that the power use constrains our future. Even as we've made more and more efficient transistors, we use so many more of them that we simply can't afford to turn them all on. So you pay Apple, you pay Qualcomm for making really advanced systems on chip with really fast microprocessors on them, and you simply can't turn them all on. 7 nanometer in widespread production next year. Over half of the die will be dark, even at desktop power levels, 125 watt power limit. And if we stack things together in 3D, we actually make our power problems worse. We make hotter hotspots. So power is pushing us towards designing systems where we only turn some of the transistors on, because otherwise it's going to melt, where we thermally limit what our processors are doing in order to fit into the power budget. That seems pretty bad. But we also have an economic problem. So there's no immediate physical limit to scaling from today's processors. We've got lots of chips built in volumes at 28 or 20 nanometer. We've got 14 nanometer, there's a little star there, in production. AMD and Apple have 10 in production. Huawei, Samsung have a little, all have 7s and 5s in development. But it's getting really expensive to do this stuff. There's no physical limit, but by God, it's getting hard to do this. And we have a lot of the planet's best brains working in this area, so it will improve, but this is sort of the end of Moore's law. Only some things will be worth the greater expense of process geometries smaller than 28 nanometer. And luckily, some of those things are shiny toys made by Apple and desktops and laptops powered by AMD or Intel processors. But there are going to be lots of things where we can't afford the higher cost of the transistors and process development. And this is having an effect on the fab plants themselves. Oh, but that's the next slide after this one. Those star marks that I've been putting on the slides. So when we were talking about 6 micron, 3 micron, even 0.13 micron processes, there was a definite thing that you could make something that was that size. It wasn't a transistor. On 6 micron, a transistor is much larger than a 6 micron thing. That's the smallest dimensions of it, the smallest part of a transistor that you could make is more what you think of when you think of 6 microns. And we've been designing transistors in exactly the same way for a very long time, where we put down a source and a gate and slap a piece of metal across the top of them, and that was a transistor, and it's flat. And in order to make better transistors, as the gate became very small, we needed to change that and make this thing called a FinFET, a vertical fin sticking up. Yeah. I'm looking in the mirror the wrong way around. And wrap the gate around it so we can increase the gate area in the dimensions. And so that there was now very little relationship between the structures we could lay down on the silicon and the actual area of a transistor when you looked at it from the top. And so the industry started making up new names for the process as if we still used flat transistors. So the first company to make a FinFET process was Intel, and they called their process 22 nanometer. It's a FinFET made with a 28 nanometer process. And then we've got 14s and 16s, which are both 20 nanometer FinFETs. And we have 12, 10, 8, 7, 6, 5, and in research 4 and 3. And these names have become marketing names. And the way Intel's marketing works is different from the way TSMC, say, or Samsung make up the names. It's just a bunch of marketeers. So that's what the star marks mean. None of this stuff is as real as it used to be. It simply reflects that their marketing believe that for a certain circuit, because you can put in more transistors when you move them into FinFET in the vertical dimension and hence make the horizontal dimension smaller, that represents a gain in process density. But of course, for different circuits, the gain is different and it makes it very hard. But it really is hard. So in order to maintain Moore's law, it takes 18 times as many scientists as it did in the 1970s. So they must be really depressed people. They're 18 times less effective than their predecessors. And you can measure it on an annual basis. Research productivity is declining at a rate of about 6.8% per year in the semiconductor industry. You could say that we're running out of ideas. Well, the ideas are getting harder to find and exploit. That's the real takeaway. Predictions are very hard to make, especially about the future. In April 2002, the head of Intel predicted that we'd have 30 gigahertz, 10 billion transistor chips by 2010. Those of you who can remember 2010 will have noticed that we didn't have them. And those of you who can remember 2020 will have noticed we still haven't got them. And we've seen some of the reasons, the power thing, why that didn't happen. In hindsight, we can look back. This is Intel's predictions in 2010. So they were just about to introduce the very first FinFET transistors in 2010, 2011, in the thing called 22 nanometer. They said our limit to visibility goes out about 10 years. So in 2013, that's right round the corner, we'll have 15 nanometers. In 2015, we'll have 11 nanometers. In 2017, 8 nanometers. In 2019, it will be smaller than that. There are all sorts of things that we can do. This is what actually happened. In 2019, the thing that was right round the corner of the release of 22, they were a year out on that as their prediction. 14, they were several years out. 10, they claim to have made their first 10s in 2019, but it's still not available in volume and it's limited in market space of applicability even today in 2020. And 7 nanometer, they're saying 2021, 2022, who knows? It's hard. The best company in the world has very limited actual visibility. There's another economic aspect to all this. As it gets hard and as it gets more and more stupidly expensive to build a fab, the green line is how much it costs to actually build a fab. The blue line is how much it costs to develop the process that your fab is going to do. When we made Firepath back at the beginning of the 2000s, there were 22 companies that were capable of making it in 130 nanometer. Nowadays, there are only 4 companies left doing 16 and 14, the main volume, and only 3 companies doing 10 nanometer. It's too expensive. You have to be really, really sure that you can do this stuff, or be the £1,000 gorilla in the marketplace, getting most of the revenue you can afford to develop fabs. So today's leading fabs, these are all 6 that I could class as leading, where you could make something reasonably high performance. Intel at the top, with their chart of Moore's Law sadness, 2015 through to 2019, all on 14 nanometer. They claim 10 nanometer at the moment, and it's only available in very limited situations. Samsung and TSMC racing each other. TSMC currently slightly ahead in introducing things. You have to ignore the names on the slides because they're made up by marketeers. Significantly, Samsung and TSMC are doing this thing which is labelled EUV on this slide that Intel haven't started doing yet. And then Global Foundries were the most recent company to drop out of the race. SMIC and UMC. The easy thing to remember, SMIC is easiest thought of as semiconductor manufacturing in China, whatever its actual name is. They are trying extremely hard. China has a pressing need to detach itself from Western designed infrastructure, but even so, SMIC are quite a way behind the top three, or even Global Foundries, and United, UMC are even further behind. And so let's look at what they're making and see what you get. Now, I did mention when they're talking about names that there's a lot of variation. Even if we translate to the number of transistors per square millimeter as a way of comparing where they are with these names, it's sort of not fair because different types of structures, different ways of building SRAM or logic scale differently with different process restrictions. So TSMC are undeniably in the lead. They're making a process that they label 5 nanometers, and that they're running samples on that, and they have volume on their 7 nanometer process. Intel have a 10 nanometer leading edge process and all their volumes on 14. Samsung are making a thing that's called 7 with 6 and 5 coming. And the table tells us the story that, you know, whatever the process label is, they're pretty close up to 2019. Well, no, Samsung and TSMC are pretty close together. Intel, with their lag on 14, the number of transistors per square millimeter did fall behind. If you count Intel's 10 nanometer number in 2019, they caught up, but then fall behind immediately that TSMC and Samsung can go to 5 nanometer. So that sort of goes some way to explaining why AMD are resurgent, because the AMD processors are now made by TSMC. Everybody has to use the same machines. So here's another look at Moore's Law, decorated with pictures of the lithography machines that make it. So chips are printed, like printing a photograph. No, not really like printing a photograph in terms of putting it through a printer. They're printed like making a photograph, exposing something to light in the first place. So in the early days, lithography machines were quite small. Think large office photocopier size. Those are the machines, sort of things on the left. And then as the demands on the lithography machine, and in particular the wavelength of light, became more stringent, the machines had to get bigger and bigger and more expensive till you get the machine on the far right, which is the modern processors. And on the left, you can see another view of where people are in terms of where the limits of using lithography machines is. So the volume machines at the moment, the machines that Intel are using, use 192 nanometer wavelength light, so-called deep ultraviolet or DUV. So you can mostly do things using optical processing with that. And there's a lot of trickery. 192 nanometer light, if you want to build something that you could call 28 nanometer or 20 nanometer, you can see you now need to print things that are smaller than the wavelength of the light that you're using. And you'll realize that that's quite a hard problem. And it's solved by restrictive layout rules plus use of many more masks than you might have thought of. So this thing called SADP limit is the self-aligned double patterning limit. You're using twice as many masks to make the feature. And you can go to self-aligned quad patterning and make things smaller, but that's much more expensive. Masks are very expensive to make. And if you want to resolve smaller features still, you'd like to have smaller wavelengths of light, extreme ultraviolet, EUV. So that's 30 nanometer, 31 or 33 nanometer, depending on how you count it, wavelength light. How do you make such light? Well, the answer is clearly a Star Wars particle beam weapon. You remember seeing all these Star Wars movies where the spaceship is exploding in space by laser beams? Well, that's what a extreme ultraviolet source is. So we have a vacuum, we have our outer space, we have a droplet generator where we melt droplets of tin, and the droplet of tin falls, since we're not in a weightless environment, it falls downwards, and we vaporize it with a megawatt CO2 laser. It vaporizes in an appropriate shower of sparks. Spaceships being shot up in Star Wars movies do, and radiates all frequencies of light. Most of the frequencies of light we don't want, so we collimate them away and extract only the most actinic, the extreme ultraviolet light to come out of the end. So with our megawatt laser, we are developing something like 200 watt output beam power in terms of the energy per square centimeter of the beam, and we're happy. Of course, every now and then we have to stop and clean all the vaporized tin off the inside of our vessel, but we can make 30 nanometer light. As you can appreciate, it's quite complicated, and the EUV scanner, the EUV source, is just enormous. So here's a handy person at the left-hand side beside two generations of EUV source. The white line is the first one, and the bigger machine is the one that's coming. And remember that the megawatt laser is underneath the fab floor. If we look at the previous picture, there's the fab floor going across, supporting our vessels, and the megawatt laser is below it on the sub-fab floor. So that isn't even all the machine in this slide. That's only the top bit that you happen to be able to see. Now, unfortunately for Donald Trump, trying to restrict the flow of high-tech devices, these scanners are made by a European company. So anyway, with such machines, we can make really small transistors. Hence, we can make as many microprocessors as we like, because they're all really small, even complicated ones. So, as I said, your smartphone chip, you've got those big apps processors that you paid for, but practically every subsystem, and there are dozens and dozens of subsystems in that SOC, also has a controlling microprocessor, and I describe it as uncountable. You could sit down and count it, but nobody ever does. So you have heterogeneous microprocessors, special purpose microprocessors all over. You have graphics processors, signal processors, etc. So there's lots of work for people who design processors and system on chips, and even more work for software people to program this assembly of things and make it work properly. And even with all of this and all our EUV, performance related to scalar programs just isn't increasing. And costs have stopped falling and are now rising, with a ever decreasing number of people being able to pay for the most expensive processing. There's quite a force to making your shiny toys cost more. And here's some trend data showing the same 40 years, but this time reporting lots of things. So you can see the number of transistors obligingly following Moore's law in the little brown triangles, but single thread performance is fairly tailed off, frequency tailed off, power hits a power wall, number of logical cores you can see rising at the bottom of the graph in the black dots, but that isn't helping. The more cores you put in only causes slight changes, unless you're interested in true parallel stuff. Now we can continue. We can use more transistors than we do today. So where are we today? Leading designs are all superscalar out of order processors, and we're at about 6 operations peak per cycle on average. So Intel have a long trend leading back to a processor that was internally called Haswell. So it's gone Haswell, Broadwell, Skylake, Kaby Lake, Coffee Lake, Refresh, Ice Lake, and probably Ice Lake Refresh before we get onto any of the comments. AMD's Zen, Zen 2, Apple's Twister, Hurricane, Monsoon, Vortex, and Samsung also dabbled in this area with a processor called Meerkat M3 and M4. They all hit this sort of 6 operations peak per cycle area. And superscalar out of order isn't particularly energy efficient, but because all communication is highly local within the design, it can be made to run quite quickly, 4 gigahertz plus. But if you're trying to get beyond 6 operations per cycle, it's very tricky. Going to 7 operations per cycle gives you only a small improvement, but things like the bypass network that connects the results of all execution units to the inputs of all execution unit gets much more difficult. At 6, the bypass network is sort of order 36. At 7, the bypass network is order 39. So you've got a tiny gain, a 1/6 gain, nearly a doubling in the bypass network. So it's very hard to get out of this hole. Nevertheless, people are trying. I suppose, yes, nevertheless, people are trying, and that's in the future. But here we have pictures of them all. These pictures of ARM cores with a backdrop of Intel's first 14 nanometer core. So these are all in processors that are called 14 nanometer, at least by somebody. So Broadwell, the first Intel 14 nanometer core, is another of the Haswell, Skylake, Kaby Lake type generation of processor. Intel have quite big processors, 11.6 millimeters squared when it was introduced, and many competing processors in 14 are much smaller. The Cortex A72, Samsung N1 and Qualcomm Cryo, which at that time really was a Qualcomm design, are significantly smaller and not greatly slower. Apple spent a lot more effort. The Hurricane processor found in iPads and iPhones is still substantially smaller than Broadwell, but in the same power envelope, hurricane catchers and in some cases passes Broadwell. Apple have done a really good job on their microarchitecture. If we look at them in 10 nanometer, with Apple's Monsoon catches and passes Intel Skylake, power for power, and it's substantially smaller. Samsung, depressed by their initial low showing, put a lot of area into their Meerkat processor and didn't catch Monsoon, let alone Skylake. A75, ARM stuck to their guns, making things about the same sort of size. It was quite a lot better in performance too. And obviously smaller cores, A73, Cortex-A55, Apple's Mistral, their low area, lower compute, higher power efficiency processor are a lot smaller. So let's talk about big and little. So if out of order superscalar is power inefficient but high performance and you have to have one, for your power budget, when you can get away with it, when the operating system thinks, oh, okay, I need to do that, but I don't need to do it really, really quickly, I'll do it in a really power efficient way, you'd like to run on a different processor. So since you can have extra transistors and build your little processors, it's a good trade-off. You can get a much more power efficient average power point. So Apple tread their own slight furrow. Their little processors are still quite big ones, big out of order, high performance capable, but they're all, the little cores are much more efficient than the big ones. And of course, you're not limited to simple relationships between the cores. So over time, where people started off with either too big, too little, or 4 big, 4 little, you now evolve to a world where the software is caught up. You can have 2 big, 4 little, or 2 big, 6 little, a mix of 2 big, 2 middle, and 4 little. Or nowadays, seen in Qualcomm devices, you can have one super big core, they call it a prime core, and then 3 ordinary big cores and 4 little cores. And the key to all this is it gives the operating system control of the power efficiency. So, as I say, that translates to a less hot chip for the same overall workload in total, provided you don't care about getting it done as soon as possible. Intel are the big holdout against doing it like this. Their chips tend to run extremely hot and then stop and cool down. And if you wanted the result, and it could be done in the time it ran extremely hot and then cooled down, that was good. And if you wanted results continually, that was bad because it slowed down a lot. You can also look to unconventional designs. There are a lot of unconventional designs because big, out of order superscalar processors really are power inefficient. So there's a whole cluster of designs around very long instruction words. NVIDIA have proprietary designs, Denver and Carmel, which are very high operation count VLIW processors with hardware and JIT converter from the ARM instruction set. So instead of building a processor that directly executes the ARM instruction set, they build a processor that executes something that they can build in a much more power efficient way, and they dynamically convert the ARM instruction set to it. But VLIW is all over high performance signal processing. So Qualcomm have a processor called Hexagon, Qualcomm have its Firepath and VASIP. Sabre have X and XC, Tensilica have BBE, TI. One of the originators of VLIW have a large number of VLIW processors. A company called Mill Computing is preparing a VLIW-like machine. It's more like a VLIW machine meets a stack machine. It has many, many novel features. All of these things have pretty much the same problem as high operation count out of order superscalars, which is bypass networks. The more results you can produce in a cycle, the more you find it a problem that you have to communicate them to other execution units. And mill computing in particular are being very aggressive here because they're going for operation counts around the 30 level. So we all predict that mill computing won't be able to run very fast, but on the other hand, 30 operations per cycle is a very high number. If they can run at a gigahertz, they might well significantly outperform many machines. And then what we compute is also changing. So we've seen many things move from general purpose computers to processors that were somewhat augmented to doing signal processing operation to now widespread use of specifically designed signal processors. And we've seen the same evolution in graphics processors. So we have special purpose computing running along all the time. But special purpose computing has now exploded into the headlines because we have deep learning engines. And deep learning engines have several advantages that makes building systems that execute them much easier. So signal processors and graphics processors have begun to break out of the scalar programming world and accept penalties in exchange for running parallel much more quickly, because they often had explicitly parallel tasks to do. With deep learning, that is amplified many-fold. So deep learning engines do 8 or 16-bit or even smaller, 4-bit, 2-bit, 1-bit processing. They can be integer and they can be massively parallel and use this parallelism successfully. Particularly one part of the field, convolutional neural networks, which do lots of convolutions, you can virtually without limit extend the parallelism. So instead of having, say, 30 operations per cycle, something like the Google TPU has 64K 8-bit integer multipliers running every cycle. So every clock tick, 64,655 V6 multipliers are done, and you can use this parallelism in the deep learning field. Coming with that, these microarchitectures are far more power efficient. So when we're saying out of order superscalars aren't very power efficient, we're in a world where they're 5 to 20 watts for about 4 or 5 gigahertz worth of computation. And here you're looking at something that's 3 to 5 teraops instead of gigaops per watt. And there's, in the future, there look to be ways to make this even more power efficient. So things called spiking neural networks, we can move our computations away from the digital binary reproducible world and start using analog structures, and hence make it even more power efficient, though a bit woolly at the edges. So in this particular field, there seem to be easy pickings almost without limit, and there is a gold rush in architecture evolution of designs that do this. Many people have obviously been bought by Intel. So if we look at a system on a chip, this is NVIDIA's, you get zillions of processors, uncountable processors, and you get lots of transistors. NVIDIA just released their latest information about their next chip, so I haven't had time well, they haven't even released pictures of it, so I can't get a sample. But the next generation of this chip, they go from 9 billion transistors to 50 billion transistors. And in there, you get an enormous number of special purpose processing engines. So you get GPUs, all sorts of custom video processing. You get special purpose units for doing deep learning, and you get special purpose units for running all that old programming stuff. So that looks reasonably impressive, and as I say, the next one along is 54 billion transistors. Innovation continues. Who knows exactly what will happen on this slide. So Intel are confident that we can keep going. It looks to me on this slide that the rate of doubling is still slowing down. That long period on 14, they're unlikely to meet these expected transitions from 10 to 7, but they're going to try, and these processors will definitely be better. To get there, we're going to have to change transistors again. So where we are today is the vertical FinFET, where the height of the fin, the depth of the fin are shorthand ways of thinking about how much gate contact area we want. So we can either go to nanowires, where we wrap the wires around, we build nanowires, we wrap them around with the gate, and thus increase the gate contact area again. Or we can go for nano sheets. Nobody's quite sure, but probably nanowires will happen. We can also recognize that we build logic with complementary transistors, a transistor at the top pulling the signal up, a transistor at the bottom pulling the signal down again, rather than a single transistor and a resistor, as was used much earlier in development, so that we could probably develop a stacked FET as one element. So building a complementary FET and pushing the two things together into one element would also be a further densification to get down in apparent process size. And of course, like the transition from planar transistors to fin transistors, this is independent of the development of smaller process geometries. The fakeness of process identity numbers can only increase through this. Now, with the cost of transistors on the most advanced processors being so expensive, because the process themselves is so expensive, and because the cost of developing it and building the factory was so expensive, it's now cost effective to co-package designs on different silicon processors. So AMD are big pioneers here, and Intel are more in the catchy up mode. The Zen 2 Intel compatible instruction set made by AMD is using two different geometries. The picture on the bottom right, the big die in that chip is on 14 and the little dies are on 7. So only put into 7 nanometers the things that you really, really want to be there, and put everything else into a cheaper process and package everything together. Intel have the same idea, but in 3D, or 2.5D, package together things on different process geometries in order to make things less expensive. We mentioned that cooling was a problem. So at present, we cool the external package if we could cool die directly, that would be more efficient. And there's a lot of research going on where you package a little thing so that you can get liquid directly onto the silicon die. So pump liquid, not water, in and out to take the heat away. How to cool it when you've put 3D stuff together remains a problem. And the last thing that's happening is wafer scale integration. Some of you may remember earlier attempts to do this. This company have built a really large chip. He's holding essentially a single thing. So where on a single yieldable die, NVIDIA have managed to pack 50 billion transistors, these guys have managed to build on a much less expensive process 1.2 trillion transistors on a 46,000 square millimeter silicon die. And naturally, it's to do deep learning. It has 400,000 optimized cores, 18 gigabytes of on-chip memory, 9 petabytes of memory bandwidth internally, because there's an awful lot of replication internally. And they can make this. Be mindful of the power. You're not going to see things like this even in a desktop computer anytime soon, because this wafer by itself consumes 25 kilowatts when operating. In order to make this thing usable, they have to mount the wafer scale processor directly on its custom designed cooling system. So that is the end of the formal bit of the talk, and if Quentin can do questions, we'll try and answer them.
Thank you very much, Sophie. That was intriguing. I certainly learned a lot. I will learn even more, I'm sure, when I go back and watch the recording a second time. It is, I know, difficult and exhausting to do this without getting feedback directly from the audience, but I can tell you we have been getting lots of feedback. We have lots of questions. I'm afraid we probably only have time for a few of them, but thank you particularly to Rob Mullins, who's helped me collate these as well. We'll start, I think, with one or two slightly more general ones, and then some of them go into a bit more detail. But I think one we could start with, which has particular interest, of course, to our department and groups in the department, is do you think that security has been prioritized sufficiently through the history of computer architectures?
It depends whether you mean the successful computer architectures, which almost without exception have ignored security in favor of fast execution, or you mean all the developments done. As a thing, computer science, particularly away from America, put in an awful lot of effort of making things more secure, making ways to do it. They never caught on with the general buyers, usually because the people who didn't care about security made something that was faster, for the same money or less money, or without as many caveats in terms of taking your dusty deck of code and executing it. And since Rob Mullins is asking the question, we can say that Cherry is yet another attempt to make a secure system with fewer compromises. Mill computing are also keenly aware of security as a major issue. So Mill computing are not only trying to build their belt machine, their VLIW machine meets stack machine design, but also to make it more secure. They recognize people will have to port stuff to their design and think that if they hold out a carrot of guaranteed aspects of security, then this will make it worthwhile for more people. So yeah, there are some significant efforts being made. As long as we have languages like C around, they'll be fighting a losing battle.
Well, that's actually a very nice segue. We had a question from Andrew Robinson asking about the Firepath and saying it's got an unusual instruction set. What do people use for programming it? Or I guess to put it another way, do we need significant language innovations to exploit some of the new hardware designs?
Language innovation doesn't hurt. A lot of machine learning is being accompanied by rapid evolution in the language and processing stacks that we use to write those things. So people who would normally never have given it a look suddenly find themselves writing stuff in Python in order to get access to the Keras libraries in order to do deep learning algorithms, for example. So yes, scalar programming languages sure are holding up the world. You're damned if you don't execute them and damned if you do. So the conventional approach is to make sure you can run the scalar programming languages and then extend C with intrinsics, where you represent in C some new functions that are actually things that can be directly compiled by the compiler into your tailored instructions. And then by writing in C with intrinsics, you can tap the power of your processor with much less pain on toolchain users. They don't have to write in machine code.
Okay. Another more general one. Do you feel that school children and students these days have enough exposure to the underlying hardware, or do they not need to know anymore how this low-level stuff works? At what age do you think it's important to learn this?
The most alarming statistic is the rate at which computer architects are dying and not being replaced by younger ones. The gruesome fact is that apart from areas where there's new stuff happening, everything's architected by the same teams of individuals. Apple's success in designing high-performance ARM processors comes largely because they recruited Gerald out of ARM to do it. So there are areas where things aren't taught well enough, or there aren't enough dead men for them to step into the shoes of, and it's hard to start up in such areas. School children, it's nice for them to have an appreciation that there is understandable stuff there if you can work at it, that shows how the world is run, because particularly in the Western world, there seems to be an awful lot of ignorance of how things are actually accomplished. And it's useful, therefore, to have at least a basic understanding that things are done in comprehensible ways, and apparent complexity can be broken down and understood. But it's a long way from there to being able to design something like an iPad and the enormous stack of software that supports it, or even design a program that runs on an iPad. Most people would despair of how complicated that sort of thing is.
Maybe a couple more here. I think this was a fairly early question, so apologies if you covered it. Stephen Kelly asked, a new smaller lithography size is always initially expensive. Is there anything that makes new sizes below a certain threshold, 28 nanometers, permanently more expensive per transistor, unlike before, or will the costs come down?
The costs do come down a bit. When a process is very new, the fab itself isn't getting very good results. So the yield at the fab of each chip is quite low. And over time, you learn at the fab how to make that yield better. And hence there is a decrease in the cost of transistors. But at the same time, the advanced processors with these self-aligned double patterning, self-aligned quad patterning stacks of masks are permanently expensive compared with other systems. So give you an example. It used to be the case back in 28, 65 nanometer days that 15, 20 masks was enough. In, well, let's say in 10 nanometer, designed without EUV, you're probably looking at 100 masks. So that translates into cost in very obvious ways. Your mask making is now 10x more painful, and the number of steps in the fab where you expose each pattern onto the silicon, etch away your resist, and then move on to the next step. That all takes longer, and that's cost. And it's not going away. I suppose that there's also materials, and one of the things that is happening is we're now making our copper wires so small that they're hardly wires anymore. They're sort of very leaky waveguides. So our copper wires are so small that they function as a horrible sort of resistor. They're so small that if we use cobalt or ruthenium, neither of which are renowned as really good conductors, they don't have the same skin effects that copper does as you make them very small. So as you make them as small as the copper, they become relatively far better conductors than copper is. So you start having to use exotic materials, and the problem of using exotic materials is that you then have to start protecting the other bits against the exotic materials. So it just breeds complexity, which costs.
Two very quick ones here then, and I think that's probably enough. An interesting one's from Simon Moore. He says, do you see any signs of an alternative to silicon?
It depends on the field, really. It's interesting that several years ago I might have said, well, quantum devices aren't using silicon. However, most of the quantum device research is now done trying to get them into silicon designs, because the silicon manufacturing world is so much more advanced than anything else. So if you want to have large numbers of qubits in a quantum computer, you better have really advanced manufacturing, and that tends to mean silicon. So quantum has gone all silicon-y when it didn't really need to be. But at the same time, you could move to other materials, particularly for spiking neural networks. You can see some evidence of other materials, things like Intel's non-volatile memory division. The chalcogenides are used to make their octane memory, so phase change materials. And so you're moving memory devices away from silicon into chalcogenides. And if you use certain types of neural network, you could use chalcogenides to execute them. You could also do that with some of the ferroelectric materials. So there are other slight avenues, but at the same time, silicon remains the one that the world is spending all its research money on, and so has the best manufacturing. If you can make it with silicon manufacturing processes, you may well have several generations of win just sitting there.
Right, last question, I think, and then we'll hand back to Anne to say thank you. This came from Nitrix in the chat room. Will we ever see another significant increase in perceived performance in microprocessors? And if so, do you think it'll come from an advance in CPU manufacturing or development or software development, or maybe quantum?
Well, we have seen a significant change in the special purpose areas. So deep learning, DSPs, GPUs have all rocketed ahead in ways that are quite revolutionary compared with what you might have expected. things that deep learning has propelled are probably the most obvious at the moment. It is now routine to be able to talk at your iPad and expect it to be able to transcribe your speech. And that's really impossible under conventional approaches. Similarly, think something like Google Translate. Run it on your iPad when you're offline from the grid of computers that support things, and your iPad locally is now capable of being pointed at some text, doing character recognition to work out what the characters are, and then translate that into a different language, and then warp the characters of the different language back into the original shapes. So Google Translate represents a really staggering change in our capabilities in pattern recognition. A specialist area, deep learning, a specialist area. General areas, no, I think I'm quite pessimistic. It's very hard.
Right, thank you very much. And thank you to everybody who submitted questions. We have another couple of pages I haven't got to here. So we will maybe forward those to Sophie just for her interest. I'd like to hand back over now to Anne.
So thank you very much. I don't really have anything much more to say except that thank you for so many people to join us. There are more people than could possibly fit in this lecture room. So yeah, I think, and it's great that the technology stayed there, but thank you for a really inspiring and quite extraordinary talk. I think that this was really definitely was one of the highlights of the year, even if it had to be virtual and we can't go and have a cup of tea or a glass of wine afterwards. So thank you so much.